All right, in this video, we are talking about addition reactions of alkenes. And so if we think about alkenes, we know that they have this pi bond, and I'm just going to draw R groups coming off of our pi bond. Remember, R groups are typically substituents that are sp3 carbons. We can react with this with some reagent. I just have an XY with a single bond there. And what's going to happen is we're going to break a pi bond, and we're going to break the XY bond, okay? And we're going to make a new carbon X and a new carbon Y bond. So we're breaking two bonds and we're forming two bonds in this reaction. And so it looks like this. I've just drawn all of these lines. I'm not showing the wedge and dash here, but as you can see, we've made two new bonds. Right here, the CX and the CY. And where the X and the Y are placed is a topic called regioselectivity. So the regioselectivity of addition reactions of alkenes is actually very good. And we're going to be, later on in this course, we're going to talk more about addition reactions with alkenes. In this video, we are going to specifically talk about addition of alkenes with hydrogen halides, or things like HBr or HCl. So let's draw a reaction here. So we're just going to take ethylene. I'm going to flip it just a little like this. So I'm going to rotate it this way. And actually what we're seeing here is the filled pi bond, okay? These are the p orbitals, and we know that these are overlapping because the colors are the same on either side. So you can draw your dumbbell shape, okay? And then you can shade one half red and one half blue. So what we're going to be doing is we're going to be adding, let's add HBr. I'm going to draw a reaction arrow. Notice a reaction arrow is not indicating whether or not it's reversible. I'm simply going to make a product with this. What happens here is that we end up getting our HBr added across this pi bond. Again, we're breaking a pi bond and breaking this single HBr bond, and we're making a new CH and CBr bond. Let's draw in our hydrogens. All right, so with this mechanism, what we're going to do is we're going to take our pi bond. We know there are electrons here in this filled pi bond. So we're going to take our arrow and start it at electrons, and we're simply going to do a Bronsted acid-base reaction. We're going to pick off this proton. That means this HBr bond will break, so we're going to show it using an arrow showing the electrons between the hydrogen and the bromine going to our bromine. So this top part is the final reaction. So you have starting material. Maybe I'll write that out. You have starting material, or the starting reagents, and then you have your product. And below, I'm going to start filling in with a mechanism. So I'm going to put the mechanism arrows here in purple. So once we add the hydrogen, we know that we added a hydrogen to one of our carbons. Sorry, that's Rhodey in the background. She wants to go outside. And this carbon here didn't pick up a bond though. So I'm going to label this carbon here with red, the one that picked up the proton. Now either one, we could choose either one to pick up this proton because it's equivalent on either side. So notice that the carbon that's red picked up a proton, but the other carbon from that pi bond didn't pick up anything. So it now has a formal positive charge. Let's draw those same arrows showing down here in the orbitals. So I have here the filled pi bond, and then we have an empty HBr. It's a sigma star here, okay? And so the electrons from this pi bond are going to attack this proton. Here's our H, and this is our Br, okay? So what's happening here is we just made what's called a carbocation. Let's write that out. Carbocation, okay? Appropriate that Rhodey is meowing so much. So what happens now is we ended up making this Br minus. We still have Br minus present. And I know it's minus because our second arrow here at the top gave another lone pair to bromine. And it already had 3 lone pairs. So now it has 8 electrons and it is negative. So what's going to happen now in our mechanism is that we're going to attack this carbocation. The Br minus, I like to draw the arrow from the lone pair. Remember, these arrows mean electrons, so it's really not correct to draw from the negative charge per se. So this bromine's going to attack this carbon, and then we're going to get our product. Let me draw in on the product, the carbon that got the hydrogen, which is that red carbon. And there you have it. That's the mechanism for electrophilic addition, or this addition of HBr across the alkene. Now, what happens though if you end up getting an alkene that isn't symmetrical? Notice that this alkene has a methyl coming off it on one side and the other side just has hydrogens. Well, there is a rule for this, which makes it nice and simple, but I'll show you why it works, and that way you can understand it for whatever system you have, because most of the time we don't have these really simple alkenes. This is called Markovnikov's rule for its regioselectivity. Regioselectivity is telling us where this H and where this bromine are going to add. In HX addition to alkenes, the hydrogen atom attaches to the carbon with the most hydrogens. The X atom attaches to the carbons with the fewest hydrogens. So as you can see, all you really need to do is remember one of these, and you'll know the other one is opposite. So the hydrogen is always going to add to the carbon with the most hydrogens. So if it has lots of hydrogens, it's going to get more. It's one way I like to think about it. So what we're going to do is we're going to draw the mechanism. We're going to start our electrons at the pi bond. We're going to attack the proton here in this Bronsted acid-base reaction. The electrons between the HBr are going to go to the bromine. So I'm going to add my hydrogen here. Now, I didn't have to draw that. We can kind of assume that this carbocation is also the same as this. We always assume those protons are there, but for the purpose of us learning this mechanism, I'm going to draw it in. So we have a hydrogen there, and we still have our Br minus around. Now, the next step of this reaction is actually more like a Lewis acid-base reaction. I'm going to write RXN for reaction for step 2. For step 1, this was more like a Bronsted acid-base reaction. Although this reaction looks so different than any of the acid-base reactions we've done, you're using the same principles. So in this next step, so for step 2, let's draw our arrows here in purple. So step 2, we're going to have our Br minus attack this carbon. Now, I wouldn't draw it to the carbocation, this positive charge, because we're actually attacking the atom. Remember, the formal charges are just there to identify what the electron count is. So once we do this step, we end up getting our product, which looks like this. Now, I don't have to draw the hydrogens in, but we could. If this hydrogen here is red, here she is again in red. I don't know why the hydrogen is a female, but she is in this video. There she is. So notice again that the hydrogen added to the carbon that had the most hydrogens in the first place. This alkene had 2 hydrogens on this end and 1 on this end. So the first arrows are the same no matter where you place it, but notice that the carbocation is on the most substituted side. This is a secondary carbocation. Secondary carbocation. It has 2 things other than hydrogens that are bound to it. In this case, 2 methyl groups. And the proton here added on the least substituted side, or the carbon atom with the most hydrogens. You could imagine that HBr could form a carbocation with this alkene this way, right? But again, our hydrogen needs to add to the side with the most hydrogens. It needs to add to the carbon with the most hydrogens. So this does not happen. We don't make a primary carbocation. I'm going to put a big unhappy face. These don't form. Well, why don't they form? Why are these so regioselective? These additions to alkenes are very regioselective. Very good at forming pretty much just that one product. So this bottom reaction, where it would end up getting the bromine here on the end, it is not observed, so it does not form. Really has to deal with how stable that cation is. Okay, the carbocation that we form, you'd imagine in the mechanism, if it's really unstable, it's probably not going to form. It might be too high in energy, and that's exactly what's happening here. So carbocations are labeled as follows. So if you have some kind of an R group on a carbon, and it has 2 hydrogens coming off and this positive charge, this would be called a primary carbocation. If our carbon had 2 R groups on it and 1 hydrogen, this would be a secondary carbocation. And if your carbon has 3 R groups and lots of friends on it, this would be a tertiary carbocation. Let's think about the stabilities here. So, the stabilities for these carbocations are as follows. A tertiary is much more stable than a secondary, which is much, much more stable than a primary. And if you want to get really, really, really unstable, you can have a methyl cation with only hydrogens coming off of it. And I don't think I can draw enough way stable. It does not form. Or CH3 plus is like really not going to form. Well, why is this? Well, it has to do with a concept that we've talked about before. This is hyperconjugation. Notice that as we add more R groups to the carbocation, it's more stable. So I'm going to draw an arrow here. Stability of carbocation increases. So in our previous example, when we reacted this with HBr, this one propene, we could either get the hydrogen adding in the middle carbon, which would be anti-Markovnikov, probably spelled that wrong, or we could add the hydrogen Markovnikov. I'm going to write Markov so I won't misspell it again. So If you look at these two differences of the reaction we just did earlier, this one is a primary carbocation, this one is a secondary carbocation. The only difference here is that there's more carbons bound to the carbon with a positive charge. The substituents add stability by a concept that we've talked about. It's due to hyperconjugation. These R groups have these hydrogens here on the end, and we know that the filled sp3 bonds with this hydrogen donate electron density into this carbocation. Carbocations exist in an empty p orbital. Let's talk about this in detail. So here I've got a simple methyl cation, the ones that we don't want to form. CH3, really unstable. And what happens is that this carbon here has this empty p orbital. Notice here that there's no benefit of this hydrogen being on this carbon. Now, if we move over to a carbon that has 3 methyl groups attached to it, you could just write CH3 if you'd like. I'm just drawing them out here. And this carbon's coming forward, okay? So carbon bound to a carbon, and this carbon's coming forward, and this carbon's going back. This is a carbocation, both of these are. We have an empty p orbital. And notice the difference here when we have hydrogen versus when we have a substituent that has CH bonds. Remember, hyperconjugation involves this CH bond donating electron density into an adjacent orbital. And in this case, this is stabilizing this carbocation. So the interactions, partial electron donation between the sigma CH, which is this guy right here, and the p orbital, which is this large green and yellow orbital here, can stabilize carbocations via electron delocalization. This isn't the first time we've talked about hyperconjugation, and it'll keep coming up. It really explains these phenomena. And in this example, it's really clear that because of these additional CH bonds that are right beside or alpha to this carbocation, this carbon with an empty p orbital, that carbon with an empty p orbital is more stable because this filled CH bond is donating electron density into that empty orbital, stabilizing it. That way it can kind of wait around for a little bit until a Lewis base or something that has electrons can go and attack, okay? Let's do a practice problem together. Let's look at 1-butene. I know, it's not that much fancier, but it's very important we go over stepwise with some of this stuff. Let's react it with HI. Now, this is going to react really similar as HBr. By now, you could probably just guess the product. Let's actually practice that. When I look at the alkene, when I'm guessing a product of addition for an alkene with an HI or HBr or HCl, I like to draw out my hydrogens. For me, I like to circle the carbon with the most hydrogens. That means in the product, I'm going to draw everything that didn't change. I know I have 4 carbons. There's my 4 carbons. On carbon 4, I know that that got another proton. I don't have to draw it in because it went from 2 protons to 3, which means that it's a methyl. Now, carbon 3 is the one that got the I minus. So I could simply draw this as my product. It's also very useful to be able to walk through the mechanism. So let's do that. So this alkene is going to attack this H, give its electrons to make I minus. I know that H is going to add here. I'm going to go ahead and draw it in. And here's our carbocation. Notice that we made a secondary carbocation. That is more stable than if we were to try to add the hydrogen anti-Markovnikov. That would be bad. That's not stable. It's a primary carbocation. So this one wins, okay? And that's also why we have the Markovnikov rule, but it's important to know why the Markovnikov rule is even a thing. So now we have our carbocation that we wanted to form, and we know that we made I minus. Well, we have a Lewis acid. We have a Lewis base. See how everything we've learned is kind of adding on top of each other now. We're going to attack our Lewis acid. And that forms our product. So this is step 2, okay? And in step 1, we simply protonated our alkene. So there you have it. That's how you do it. Now, the reason I drew this product is because there's something really special about our product for this reaction. I'm going to erase these carbon letters. We went over carbocation stability, and we went over that it was in this p orbital. We know that these alkenes are flat. This p orbital here, or the plane of this alkene, is flat. This is sp2 hybridized, all right? They're trigonal planar. The carbocation that we have here is also flat. I'm going to draw here, I'm going to label this part as an ET for ethyl, okay? And I'm going to label this part as an ME for methyl down below. So here's my ethyl. It's bound to a carbon, and I'm going to highlight this carbon here in a red dot. Okay, here's our carbon here with the red dot there. And what's also on this carbon that I'm not drawing above is we know that we have a hydrogen. It was here, and then I just omitted it in the line structure below because we tend to not draw them in. I'm going to have this hydrogen coming out towards us. And then this is going to be going back where the methyl's at. So essentially what I've done is I've just rotated it so that way it's coming out, straight out towards us. And I'm going to draw this p orbital. This is our empty p orbital. This structure, this carbocation, is flat. I'm going to draw that over here. This carbocation is flat. When I take iodine, this I minus, I can attack from either the top or the bottom. This p orbital can accept electrons on either side because it is in the shape of this dumbbell. There's an empty orbital portion that's on the bottom and on the top. We're not concerned about the shading here. That's just the sign of the wave function. But it can accept electrons on either side. This means that the iodine can attack from above or below. Well, what happens when we do this? Well, what happens here is that I can draw my ethyl coming here. Here's my carbon that was red, and my iodine will be on top, okay? I'll have my hydrogen here and my methyl going back. If it attacked from the bottom, It's going to kind of push this up. Here's my ethyl, here's my carbon, here's my iodine that attacked from the bottom, okay? Hydrogen and a methyl. And what you'll notice about these two structures is that these are actually mirror images of each other. The iodine is either on top or on bottom, and I'm going to depict this on the top structure here. What you end up getting is you either get the iodine coming forward or the iodine going back. You're welcome to build these molecules, and you'll see that what I've drawn above is the same thing, okay? Build models. Whoa. There we go. Build models. So you actually get two products for this reaction. If you build these molecules, you'll notice that you cannot rotate these. These are, you can't rotate them to change one into the other. They are not conformers. These are what we call enantiomers. They have a chiral center. We're going to talk about this in the next video. But what I want to highlight here is that the chances of this bromine coming from the top or coming from the bottom, there's a 50-50 chance. There's nothing that is predicting which side it will favor, because neither one is favored. 50-50 chance. So actually you get a mixture that's 50-50, or you can say a 1-to-1 mixture, okay, of these enantiomers. And the reason I wanted to bring up this reaction, this is the first reaction we've done in this class, and I thought it was useful for our next topic, which will involve enantiomers and chiral centers. All right, and I will see you in the next video.